Welcome you all to the session on backpropagation network. A backpropagation network is a type of multi-layer artificial neural network trained using the backpropagation learning algorithm. It is one of the most widely used supervised learning techniques in ANN. The main objectives of a backpropagation network are to minimize the error between the actual output and the desired output by adjusting weights repeatedly. The network learns from errors and improves its performance gradually. The learning occurs in two stages, forward pass and backward pass. In forward pass, the input signal moves forward, that is, input layer to hidden layer and then to output layer, and output is produced. During backward pass, error is calculated and propagated backward. That is, from the output layer, the output is passed to the hidden layer and from hidden layer back to the input layer. During this process, weights are updated to reduce the error. Hence, we call this algorithm as backpropagation. So a backpropagation network generally consists of an input layer, one or more hidden layers, and an output layer. So in the figure, we can view a simple architecture of a backpropagation network which has one input layer, one hidden layer, and one output layer. The number of hidden layers can be increased. So the function of the input layer is to receive the input data and it performs no computation, whereas the hidden layer performs intermediate computations and extracts features or patterns present in the data. The output layer produces the final results and output. The algorithmic process involved in backpropagation network is shown below. Step 1. We initialize the weights and the learning rate by random. Step 2. Calculate net input to each hidden layer Zj for j is equal to 1 to n. In general, mathematical representation of the input to the hidden layer is represented as Zj in is equal to W naught j plus summation I is equal to 1 to n xi wij. As shown in the figure, there are two inputs x1 and x2. So there are two net inputs z1 in and z2 in for the network shown. So z1 in will be equal to w01 plus x1 w11 plus x2 w21. Similarly, z2 in will be equal to w2 w02 plus x2 w22 plus x1 w11. Step 3. We calculate the output of the each hidden layer by applying the activation function. Generally, sigmoid activation function is used. So phi of Vj is given by 1 by 1 plus e to the power of minus a Vj, where a is the learning rate and a is assumed to be 1. For the network shown below, Z1 is equal to 1 by 1 plus e to the power of minus Zin, and similarly Z2 is equal to 1 by 1 plus e to the power of minus Z2 in. For each output unit Yk, for k is equal to 1 to p, Yk of in is mathematically represented as Yk in is equal to W naught k plus summation I is equal to 1 to n Zi Wik. For the given network, Yin is given as Yin is equal to W naught plus Z1 W1 plus Z2 W2. Now step 5. Apply the activation function to determine Yk. Y is given by 1 by 1 minus 1 plus e to the power of minus y in. Step 6. Compute the local gradient. Del j is represented mathematically as yj into 1 minus yj into dj minus yj, where dj is the target. Del 1 is equal to y into 1 minus y into d minus y for the given network. Now step 7. Compute change in weight in output layer. Change in weight is given by del wi, which is equal to eta del j zi, where eta is the learning rate. For the given network, del w1 is equal to eta del 1 z1, del w0 equal to eta del 1, del w2 is equal to eta del 1 z2. Step 8. Compute the local gradient for the hidden layer del jj. Del jj is given as zj into 1 minus zj summation of k del k w kj. Here there are two input values. So we have two gradients, del 11 and del 22. So del 11 and del 22 for the given network is represented as del 11 equal to z1 into 1 minus z1 into del 1 w1. Similarly, del 22 equal to z2 1 minus z2 into del 1 w2. Now step 9. Compute the change in weight in hidden layer. The change in weight is given by the expression del wij equal to eta del ij into xi, where del ij equal to eta del jj into xi. For the given network, the change in weight in the hidden layers are del w01 equal to eta into del 11, del w11 equal to eta del 11 into x1, del w21 is equal to eta del 11 into x2, del w12 is equal to eta del 22 x1, del w22 equal to eta del 22 x2, and del w02 is equal to eta into del 210. The new weights are computed by using the formula new weight equal to old weight plus change in weight. The formula for calculating the new weights are W01 equal to W01 plus del W01. W11 is equal to W11 plus del W11. W21 equal to W21 plus del W21. Similarly, del W12 is equal to W12 plus del W12. W22 equal to W22 plus del W22. W02 equal to W02 plus del W02. W1 equal to W1 plus del W1. W0 equal to W0 plus del W0. W2 equal to W2 plus del W2. Thus, the updated weights are computed. Now we shall see a simple example. Calculate the new weight of the multi-layer perceptron neural network. Given the values of x1 as 0, x2 equal to 1, W01 is 0.3, W02 is 0.5, W11 is 0.6, W21 is minus 0.1, W12 is equal to minus 0.3, W22 is equal to 0.4, W0 equal to minus 0.2, W1 is equal to 0.4, W2 is equal to 0.2. The target output is given as 1 and the learning rate is 0.25. The activation function used is binary sigmoid activation for the given network below. So this is a simple neural network with an input layer, one hidden layer and an output layer. There are two input values x1 and x2. So x1 and x2 are fed to the hidden layer values, where z1 and z2 are the hidden layer and the output layer is given by y. The input to this hidden layer are z1 in and z2 in. So To solve this numerical, first of all, we shall list the given values in step 1. Step 1, we have written all the given input values from x1, x2 and all the weights. And given the learning rate is 0.25 in the problem. So learning rate is determined as eta. Eta is equal to 0.2 and the target is specified as 1. Target is denoted by the letter D. So D is equal to 1. Step 2, we compute the inputs to the hidden layers, that is Z1 in and Z2 in. Z1 in is computed using the formula W01 plus X1 W11 plus X2 W22. By substituting the values, we get Z1 in is equal to 0.2. Similarly, Z2 in is calculated as W02 plus X1 W12 plus X2 W22. By substituting the values, Z2 in is obtained as 0.9. In step 3, we apply the activation function to the input values to the hidden network and determine Z1 and Z2. Z1 is calculated using the formula 1 by 1 plus e to the power of minus Z1 in, which is nothing but the expression of the sigmoid activation function. So the value obtained is 0.5498. Similarly, Z2, we apply the sigmoid activation function to obtain the value of Z2 as 0.7109. In step 4, we calculate the input to the output layer, that is represented as Yin. Yin is calculated using the formula Yin equal to W0 plus Z1 W1 plus Z2 W2. By substituting the values, we obtain the result as 0.09101. In step 5, we determine the actual output again by applying the sigmoid activation function to the input to the output layer. So y is equal to 1 by 1 plus e to the power of minus yin, which is obtained as 0.5227. Now in step 6, we go for the back propagation process. So to determine the gradient function. So del 1, in the first step, we determine the back propagation from the output layer to the hidden layer. So there is only one output layer. So we determine only del 1. That is one gradient function is there. So del 1 is equal to y into 1 minus y into d minus y. So substituting the values, we obtain the resultant as 0.1191. In step 7, we apply the back propagation from the hidden layer to the input layer. So here we determine the change in weight. So del W1, del W0 and del W2 are determined using the formulas eta del 1 is Z1, del W0 is eta del 1, del W2 is eta del 1 is Z2. And the values obtained for del W1 are 0.0164, del W0 is 0.02978 and del W2 is 0.02117. Now in step 8, from the hidden layer to the input layer, we are calculating the gradient function, that is del 11 and del 22. Del 11 is equal to Z1 into 1 minus Z1 into del 1 W1. Similarly, del 22 equal to Z2 into 1 minus Z2 into del 1 W22. By substituting the values, the value for del 11 is obtained as 0.0118 and del 22 is obtained as 0.00295. Step 9, we obtain the change in weight for the input layer. So del W01, del W11, del W12, del W21, del W22 and del W02 are obtained respectively in this step. In step 9, we determine the updated weights for W01, W11, W21, W12 W22, W02, W0, W1 and W2. So the updated weights are calculated respectively using the formula old weight plus change in weight for all the weights. The values are being determined. This is how the weights are being updated in the back propagation algorithm process. Hope you have enjoyed the session on back propagation network. Thank you.